So as the particles move from one place to another, there is a motion, and whenever there is a motion, there is kinetic energy. So kinetic energy and sound or heat energy. So that was for the first one. The pieces fall an average distance of 1.2 meters during one turn. The total mass of the metal pieces is 150 grams. All right. So first of all, what I'm going to do is I'm going to convert 150 grams into kilograms because kilograms being the standard unit of mass. And if you're calculating the energy, then in order for your energy to be in joules, your mass should be in kilograms in the first place. So it would be 0. I can write it direct here, 0.150 kilograms. All right, we can convert it into kilograms. Calculate the loss in the gravitational potential energy of the pieces as they fall once. The gravitational field strength G is 10 Newton per kilogram. So that should be an easy one. We can simply use the formula for loss in potential energy. That equals mass times gravitational field strength times height. And that would be 0.150 times 10 times 1.2. Then we hit it on the calculator and we'll see what's the answer for this one. 1.8 joules. This is what we get when we hit it on the calculator. So I'm just going to write here 1.8 joules. All right, so the next part 2 says a student turns the table quickly after small metal pieces have fallen from one end to the other 80 times. The temperature has increased by 7 degrees Celsius. Determine the specific heat capacity of the metal. So we need to find the specific heat capacity. So the formula relating the specific heat capacity and the energy we studied already. It is written as Q equals mc delta theta, and the alternate notation is um, sometimes you can also write it this way. Instead of representing heat by Q, you can represent heat energy by E, and then it would be E equals mc delta T. Delta T would stand for temperature. Some of the textbooks they use delta theta, some of them use delta T, but in our O-level physics syllabus they generally prefer this one, right? But we should be aware of both of them. Determine the specific heat capacity of the metal. So we need to find is the value of C. We need to find this thing, the specific heat capacity. So what I'm going to do is I'm going to rearrange the formula for C, and that can be written as C equals E divided by M delta T. Right, delta T stand for the difference in temperature, the change in temperature. So now we need to plug the value of the energy, and then we need to plug the value of mass and the value of change in temperature. So what we can do is what we can do here is we know all right, so let's think about the energy. After the small metal pieces have fallen from one end to another 80 times, so that means the loss in gravitational potential energy, which was 1.8, we have to multiply it by 80. So we get the total energy loss by all those movements, the total energy loss that would take place in all those 80 times. So that would be 180, sorry, 80 times 1.8, 80 times 1.8 divided by mass. The mass was once again, it was given somewhere. Yeah, 0.150. It has to be in kilograms. Once again, 0.150 times the change in temperature was 7.0. And we hit it on the calculator as it is, and let's see what we get there. And we'll be trying to write the answer in two significant figures because the entire data was in two significant figures. All right, so we get 137 something, and if I convert it into two significant figures, that would be 140. 140, and then the unit of specific heat capacity would be, you can, if you don't remember the unit, you can just obtain it from here because the energy would be measured in joules. Then we have everything in the denominator, two things in the denominator, and those two things are mass, which would be measured in kilograms. So you can write kg here, kilograms, and the temperature we are measuring in degrees Celsius. So both of them are in the denominator. We got 140 joules per kilogram times Celsius. Now in the second part, the third part, sorry, the student repeats the same experiment. He's turning the tube vertical. He's turning it, making the what we had there masses fall on the other corner, but he's doing it slowly. Thermal energy or the temperature of the tube increases. Alright, so here we have the next one. A hot steel rod is cooled by plunging it into the cold water as shown in figure 3.1. The steel rod has a mass of 2 kilograms and its initial temperature of 500 degrees Celsius. It cools to 50 degrees Celsius when placed in the water. So let us write down the data that we get from here. For example, we get the value of mass, we get the value of delta T, the change in temperature. So the change in temperature from 500 degrees Celsius to 50 degrees Celsius would have been 450 uh, degrees Celsius. Then you have the specific heat capacity of the steel is 460 joules per kilogram degrees Celsius. Calculate the thermal energy lost by the steel as it cools to 50. So you have the standard formula you need to apply. E equals mc delta T, or we can also write it Q equals to mc delta theta. Both notations are acceptable. Then we simply need to insert the values. Mass should be in kilograms. It is already in kilograms, 2.0 times specific heat capacity was 460 times the change in temperature was 450. Then once again, we hit it on the calculator and the answer should be in two significant figures. 1, 2, 3, 4 joules. And once again, like I said, that's a very good practice. Whenever your answer is greater than 10,000, you better write it in standard form. That would be 4.1 into 10 raised power 1, 2, 3, 4, 5 into 10 raised power 5 joules. Yeah, 4.1 into 10 raised power 5 joules. Moving on to the next one, part B says a small mass of water boils when the rod is placed in the water. The remaining water then cools to room temperature and some of it evaporates. In both boiling and evaporation, water molecules escape into the air. State one way in which boiling is different from evaporation. So this is a very general question, and they ask you a lot of times, and also a very easy one. So you simply say boiling occurs at a specific temperature, that is a boiling point. However, evaporation can occur at any temperature. The next one, then we have the rate of evaporation decreases as the water cools. Explain why this happens using the ideas about molecules. So this is how you can phrase this one. High energy molecules escape from the surface and we are left behind with less energetic molecules. Hence, the average kinetic energy of the molecules decreases. So you're assigned 2 marks for it. One of the mark is for uh, commenting about the average kinetic energy of the molecules. Will it increase or decrease? And the other mark is for mentioning the reason, like why the average kinetic energy of molecules would decrease. Yeah, so liquid in glass thermometers use the expansion of a liquid to indicate the temperature. Part A. Figure 9.1 shows the molecular structure of a solid. On the left side we have a solid, and on the right side we have the molecular structure of a gas. In the middle box, part A says, in the middle box of figure 9.1, sketch a diagram to show the molecular structure of a liquid. So the structure of a liquid would be in such a way that the molecules are not too close as they are in solid, and they're not too far as they are in the gas. So it should be something in between. And you need to be very careful with it, that the size of molecules should remain same. Right? You can't really mess up with the size of molecules. You cannot increase the size of molecules or decrease it. The only thing that you can change is the separation of the molecules. So I'll just try, let's just assume that I'm not trying to change the size of the molecules. The size of the molecules remains the same. Now the thing is, this question can be answered in different ways. There are a lot of ways you can answer this question, but these 2 points, the points that I've written here, are the ones that are the Cambridge is mostly looking for in your answer. First, now you have to mention the molecules are further apart already, and they can be narrowed down, they can be compressed, they can be brought close to each other, close to one another, and in the gases there are less repulsive forces which make them easy to be compressed. The temperature of a liquid in glass thermometer increases. State 2 ways in which molecules of the liquid in thermometers are affected. So what we're doing is that the temperature of the thermometer is being increased. What would be the effect of that increase in temperature on the molecules of the liquid? So first of all, molecules will have greater kinetic energy. Molecules will have greater kinetic energy. All right, or you can also say the molecules will be moving faster. But the thing is, these 2 points, the molecules will be having more kinetic energy or the molecules would be moving faster, are considered a single point, because kinetic energy and speed, they are directly related to each other. So you cannot break it down and write them as 2 different points. They would not be considered as distinct points. So even if you write here molecules will have uh, faster speed, they would be moving faster, that would be considered only a single point. So what we can write here is the separation between the molecules would be increased, or more separation between the molecules will move further apart. Explain why the reservoir of water in the plastic container that is at room temperature does not mix with the cold water in the tank below. So the thing is, cold water and hot water, they have different densities. Just like cold air and hot air have different densities, and hot air we study in thermal energy as well. Hot air rises up and cold air sinks at the bottom, sink towards the bottom. So likewise is the case here. The colder water is more dense, it would stay at the bottom. The colder water remains at the bottom, and hot water is less dense, it remains at the top. Alright, now practically it does not mean that no cold water molecules would move up or no hot water molecules would travel down to the bottom. Right? Practically there would be some molecules, hot water molecules, that would be indeed going towards the bottom, as and meanwhile their temperature would also be changed. So but overall, by and large, cold water molecules would remain at the bottom and hot water molecules would remain at the top. Then we have the next one. When the tap is open, water at the room temperature from the reservoir flows down into the tank. Cold water from the tank flows through the plastic pipe in out of the tap. Cold liquid from the refrigeration unit is pumped through the copper pipe and thermal energy passes through the copper to this liquid. Suggest why this pipe is made from copper. Simple answer we have for this one, because we're trying to conduct the thermal energy, and copper is a metal, a good conductor of thermal energy. So copper, being a metal, is a good conductor of thermal energy, or you can write is a good thermal conductor. That would be the same thing. Is a good thermal conductor. The next one we have is explain in terms of free electrons how the thermal energy is transferred through the copper. Okay, so for this question we can answer it this way. As the electrons are subjected to heat, or as they acquire the heat, they gain the energy, and with that energy, the heat energy is converted to their kinetic energy, and with that energy they travel a long distance through the copper metal, and in their path, as they're moving in their path, they hit the carbon atoms, and when they hit the carbon atoms or the molecules, they transfer their energy to those atoms. Those atoms start vibrating, and those vibrating atoms, once again, they transfer their energy to electrons. So this process gets repeated this way. Alright, so this is how we can answer this one. As the water near the copper pipe cools down, its density would be increased. And if the water has more density, it would sink at the bottom. It would sink towards the bottom, and the warmer water would go upward. The warmer water would move upward, and in the container, you have the cold water. The cold water would be moving to the bottom like this, and the hot water at the same time, let's say you have the hot water would be moving upward. Hot water is less dense, cold water is more dense, and that establishes a convection current. And once again, convection current can take place in the fluids, and the fluids, it includes liquids as well as the gases. Alright, then we have the next one. A tap is open and water at 21 degrees centigrade flows from the reservoir into the tank. The specific heat capacity of water is 4200, followed by the unit. Calculate the thermal energy that is moved from 250 grams of this water to reduce the temperature to 7 degrees Celsius. So this is the change in temperature. Alright, you're not provided. Alright, so the final temperature has to be 7 degrees Celsius and the initial temperature was 21 degrees Celsius. So the change in temperature, you can subtract 21 minus 7, you'll be getting 14. Specific heat capacity, the value of C is given. The value of mass is also given, but that one is in grams. You gotta make sure you convert it into kilograms by dividing by 1000, because uh, the energy would be in joules only if the mass were in kilograms in the first place. So that many kilograms. Then you apply the simple formula of heat energy, that is E equals mc delta T, or Q equals mc delta theta. So E equals, all we got to do is to insert the values in it. 0.250 times 4200 times 14. Yeah, so the answer in two significant figures would be 15 followed by 3 digits. And once again, if you want to write it in the standard form, you're very welcome. 1.5 into 10 to the power 4 joules would be the answer in standard form. Describe the motion of the molecules in a liquid which is at uniform temperature throughout. Yeah, once again, so molecules move throughout the liquid in the form of clusters. Clusters mean in the form of a group, and they'll be able to slide over each other. So state what happens to the motion of the molecules in a liquid as the temperature of the liquid decreases. So as the temperature decreases, the average kinetic energy of the molecule would be reduced. You can answer in terms of speed as well, but that would be the same thing.